Hi everyone, and welcome to our second weekly webinar for the Udacity Deep Reinforcement Learning Nano Degree. My name is William Proshek. I'm a mentor at Udacity, and I'll be presenting this webinar on reinforcement learning and the Markov decision process. So I hope that you've all had a great week learning the content, and hopefully this will go through some of the details of what you've gone through in another light. So most of the content that you would have been looking at would have been looking at the introduction to reinforcement learning and the Markov decision process, and then how to apply that to the problem and the solution. So basically, what I'll be covering in this webinar will be, I'll be going through just the basics of reinforcement learning, sort of how it fits in. Some of these things I covered in the last webinar briefly, but I'll be going into them in more detail today. So sort of, what's the difference between reinforcement learning and supervised, some of the practical applications. I'll just go a bit over, say, some of the parts of it, like episodic tasks and continuous tasks, state of agent and environment, a bit more into rewards. We'll go into some categories of reinforcement learning that are good to understand. Then I'll get into the Markov decision process. What exactly is the Markov decision process? The elements to it, for example, Markov property, Markov process, Markov reward process. Go a bit more into it, and then I'm going to go into OpenAI Gym, RL, and NDP, and how they all sort of work together, and explain sort of a bit more of how to use OpenAI for applying RL problems, and which are based on an MDP. At the end, I'll have question and answer time. Basically, if you have any questions along the way or you're not sure, just post them in the YouTube chat and I'll try to get to them at the end. But I will go through all the content first and then go through any of that later on. Probably also this will be recorded. I'll post that later on Slack. So first, what is reinforcement learning? So reinforcement learning is sort of known as a semi-supervised learning model in machine learning. So the main idea of reinforcement learning, which I went a little bit through in the last webinar, is characterized by an agent learning to interact with its environment. So you can see that on the diagram on the right, there's a loop. So the main goal of this agent when it's interacting with the environment is to maximize the accumulative reward, which I'll go into a bit more detail later. So as you can see, the agent has a set of actions, and it performs a particular action, and from that the environment gives back the next state, so S at t plus 1, and also gives the reward at t plus 1. So a state could be pixels, a state could be joints in a robot, a state could be basically fully observable or partially observable. It could be many things. So it's what you can get back from the agent, from the environment. The state and reward and this loop that you see is pretty much the fundamentals of reinforcement learning, and RL is usually modeled as a Markov decision process, and this diagram explains in very simple terms, in a sense, what a Markov decision process is doing, or how it's interacting with the environment. So next, I'm just going to go over, where does artificial intelligence lie within, where does reinforcement learning lie within artificial intelligence? So as you've probably already known, and as I talked about very briefly in the last webinar, was that Reinforcement learning is a subset of machine learning, which is a subset of artificial intelligence. Machine learning is split into three main parts: supervised learning, unsupervised learning, and reinforcement learning. Most of you have probably used supervised learning, and this is what most deep learning is based on. So labeled data, and then say trying to categorize. So say the old dogs and cats. So labeled data, put through a system, and then defining what's what. Unsupervised learning is more to categorize, put together into groupings, and reinforcement learning, its main goal is to maximize the cumulative reward. And so it's more about a feedback. So probably, one of the things that a lot of people ask, well, what's the main difference between reinforcement learning and, say, supervised learning, which is the most common of machine learning techniques? So the main difference is reinforcement learning is all about making decisions sequentially. So in simple words, we can say that the output depends on the state of the current input, and the next input depends on the output of the previous input. In supervised learning, the decision is made on the initial input or the input given at the start. So, for example, one of the things with reinforcement learning, it's decision dependent. So we give labels, in a sense, to the sequences of dependent decisions. So while supervised learning, decisions are independent of each other. So labels are given to each decision. So for example, it doesn't matter what cat or dog you see first in supervised learning. It's not dependent on each other. The state that you are in a reinforcement learning problem is defined by the previous action and state, and that defines what the next state will be, which then will give you the next set of actions that you have. So reinforcement learning is really good for games like chess, where you are trying to win and has many sequences. Well, supervised learning is great for object recognition, it's classification and things like that. So pretty much, they are quite different, but you could define a reinforcement learning problem very similar to a supervised learning problem. So if you made a reinforcement learning, use a model and have just one step. So for example, you could make a pick the color, blue or red, and the reward would be +1 or say -1 or +1 and 0, depending on whether it gets it right or not. In a sense, that's doing a supervised learning task, but you've created, instead of labels, a function which is actually giving back the reward. So slightly different, but probably achieves the same results. But we don't use reinforcement learning typically in those tasks, and we probably use a supervised learning for something more like that. But if it was from a game, you could put a reward in and use reinforcement learning on a set of actions. Now, probably the main points of reinforcement learning we've sort of half covered is the input should be an initial state from which the model will start. Now, the output, there's many possible outputs as there is a variety of solutions. So, for example, you start a particular state, you might have, chess is a fantastic one for this. You start off with all the board together, both sitting in your initial positions. Depending on the action taken, for example, moving, say, a pawn up 2, it changes the next state. In a game like chess, the next state's not dependent on what you've just done, but also what the opponent does. So that could also, there's basically as many next states as there is possible actions. And for example, chess all up has, I think, a 10 to the 120, 40 possible moves. So just so many moves, it's incredible. Go has a little bit more, and I believe that the StarCraft environment, which was just sort of in a sense defeated by D9, has 10 to the 1020 something, which is just mind-boggling, since Go already has more actions than all the stars and planets in the whole entire known universe. So pretty much you would say that Go would have, StarCraft almost has infinite. Probably the other thing is the training is based upon the input. So the model will return a state and the user will decide to reward or punish the model. So when I say user, I mean the environment will, in a sense, or a crafted reward will tell you whether you've done a good action. So if you're using a financial model and your action was to buy, and it went in the opposite direction, and you sold, you'd get a negative. If you sold when it went positive and you made money, it would be a positive reward. And the reward would probably be based on how much your balance has changed. But this could be either done at each time step or different, and I'll talk about that more on how rewards can be actually defined. And pretty much the best solution is decided based on maximum reward. So the whole process, it's just trying to maximize its reward in this, in the sequence that it's doing. And typically this is sort of done in an episodic task. Now, just before I sort of go into the nitty-gritty, I'm just going to talk about some of the practical applications of reinforcement learning. So it can be used in robotics for industrial automation, which could be agriculture. Agriculture could be done in many things. We're currently looking at creating a reinforcement learning model for feeding in the agriculture industry. We're trying to find the optimal way of feeding, but first we're just going to look, in a sense, data that we collected. So one of the things that I find interesting is using RL for training people. So, for example, having a feedback loop from people learning. So, for example, you could have a quiz that you take, and based on the results, the RL agent will make a decision based on that, in the sense, state that it's given back. Maybe also based on your profile that it may have asked questions before, and it will try to make a decision to optimize your results, so to try to get you to pass. And this could be incredibly powerful for learning in the future. We could have agents to help teachers, or we could have agents that are just, in a sense, teachers themselves. One of the things that I've been using, it is for deep RL for reinforcement learning, is the financial market. So, for example, you could, in a simple model, you would have buy, hold, and sell, and the agent would, buy or sell stock or currency pairs in real time and make, and its basically task would be to optimize, once again, its balance or reward. The other thing which I can see it may be getting used a lot is in game development. So NPCs currently are usually programmed, set, how they sort of interact with you. So a lot of the times, what happens in games, what bores people, is they find an exploit on as part of the game, or part of the environment, an NPC, and basically, in a sense, it makes the game a bit boring, and other people use it. So what you could do in game development is you could have the NPCs to actually have AI agents that learn to, so say you exploit it, it would learn to find a way of not being exploited, because it's trying to optimize a way of, say, defeating you or achieving its particular task. One thing I sort of, a way of explaining that would be with, say you're fighting a game against your friend, say Mortal Kombat, Street Fighter, one of the older games, and your friend finds a good technique and it just keeps on beating you. what you tend to do is then try to find a way of stopping that. And so you, through reinforcement, are learning better ways of optimizing by winning. And so, once again, you can use this in game development, or even to generate like maps and many things. Probably one of the other aspects is, for example, autonomous vehicles, and this could be drones, cars, delivery vehicles, and they will probably use a combination of a few different techniques, but RL works quite well. I've been playing around with Donkey Car and Carla a bit recently, and yeah, it's pretty interesting what you can even achieve just from basic pixels. So that gives you just a bit of an idea. Look, basically anything that has a that you can define a reward, which is just about most things, you can use reinforcement learning for. And you'll find more things, and the industry will, I guess, find more things as we apply it more and use it in the real world. One of the things I'm just going to quickly go over before I get into it more is just categorizing reinforcement learning agents. So I'm just going to sort of briefly do this because it's part of what you'll be learning in the course. So a value-based agent agent will evaluate all the states in a state space, and the policy will be kind of implicit. So the value function tells the agent how good is in each action in a particular state, and the agent will choose the best one. So basically it puts a value to a state, to an action in a particular state. And typically what it will be doing is picking the best action for that state. And this is sort of based, in a sense, on the MDP theory, and involves, say, discounts and stuff like that. Now, a policy-based agent, instead of representing the value function inside the agent, we explicitly represent the policy. So the agent searches for the optimal action value function, which in turn will enable it to act optimally. Now, the next thing that we started to see is active critic agents. So this has a value-based and a policy-based agent, and an agent that stores both the policy and how much reward it's getting from each state. Probably other things to think about are model-based agents and model-free agents. So an agent tries to build in a model-based agent, tries to build a model on how the environment works and then plan to get the best possible behavior. A model-free agent is what you're typically going to see in most of the algorithms, is doesn't try to understand the environment, doesn't try to build the dynamics. Instead, we go directly to the policy and all function value. We just see experience and try to figure out a policy of how to behave optimally to get the most possible reward. And that's what you'll be using most of the time. Now, I'm just going to go talk about the state of agent environment. So the environment state is the information used within the environment to determine what happens next from the environment, so spit out the observation or the next state of reward. The environment state, T, is a private representation of the environment. Whatever data the environment uses to pick the next state of reward, the environment state is usually visible to the agent. Even if it's invisible, it might contain some irrelevant information. The agent state captures what happened to the agent so far. It summarizes what is going on, and the agent uses this to pick the next action. The agent state is its internal representation, so whatever information the agent uses to pick the next action. That's just an overview of that environment state in the agent environment. I'm just going to go briefly, because this is something that you've looked at this week, was episodic and continuous tasks. So an episodic task is a task that has a terminal state. So nearly all of the problems that you'll be dealing with will be episodic. And if they're not, you can sometimes define it. So some people, for example, a racing game, which we've got below, you race the game, if you crash and die or you finish the lap, it finishes, and then you start again and you do another. And that's basically an episode, which is episodic. A continuous task would be, for example, once again, financial markets. So it's just forever learning and continuing to learn new things, and just keeps on going forever, day after day after day. Now, you could frame this as an episodic task by putting a cutoff of every 24 hours or every 7 days or a year, but that's the main difference. And you'll probably find that the majority of tasks that you'll be doing will be episodic, especially at the beginning. Now, what are rewards? Now, rewards is the most important thing that the agent gets back. So it's basically its labels in a sense. So whether it knows whether it's doing good or bad. So a reward is a scalar feedback signal that indicates how well an agent is doing. So the whole agent is, when it's doing a particular task, is trying to maximize the expected sum of reward. And reinforcement learning is based upon the reward hypothesis, which states that all goals can be described by maximization of the expected cumulative reward. So if for example, if it was a financial market game, it's trying to achieve most money over a certain amount of time. If it's a game, it might be trying to maximize the score or finish the level. If it's a walking robot, it may be as it moves forwards, it gets reward, and maybe if it falls over, it gets a negative reward. So that basically will say to the agent that, oh, if I do those actions and I fall over, I get a negative reward, and also it might have even terminated the state potentially and had to start again. So it goes, no, I'm not going to do those actions when I get in that particular circumstance or state again. And it tries to optimize its actions to go forward. One of the things that I think it was DeepMind, OpenAI, do either one if I'm not quite correct, but they created a humanoid which was basically got reward for going forward. One of the things they found was that it was being chaotic and putting its arms and legs everywhere and being really weird. So one of the things they did is crafted their reward and said that it also gets a slight reward for how little amount of movement the joints go from step to step. So rather than going from 90 degrees to 180, going to 92 and then maybe 94 and then 97 will give it more reward than if it does a large movement, which is a bit like how, so in a sense being more efficient. And so one of the things that you'll find is most of the environments that you get at the beginning will give you a reward. Now, one thing a lot of people do then is from that reward is they craft it themselves. So one of the things you'll be probably doing, and you may need is to craft a reward. For example, in a game of chess, the reward is given at the end +1. And you would say, well, why doesn't it get a reward for, beating a queen? Now, you probably could do that, but the great thing about reinforcement learning is that it doesn't care about the states before that it ate it, in a sense. It's looking at the future and trying to maximize that accumulated reward. So it's looking at the current state and going, hey, if I do these things, I will win, and then I'll get my reward. And these are usually the actions leading up to that are discounted. So it's still looking at the next move, probably more importantly, but also realizes that, hey, in the future, if I do these and this particular, actions occur, I'm most likely going to win. Problem is with games like chess, there's so many possibilities that unless it's trained huge amounts, it really doesn't know, what the next action is, especially because it is completely stochastic and can be, changed by what the opponent does. Another thing is, how to define the reward. So rewards can make a massive difference. One of the things I found in doing a financial agent recently was, do I give it a reward when it finalizes a trade, or do I give it a reward at each step on the placement of that trade? Now, you probably think that it would both converge to the same spot in the end, but I actually found myself that doing it each step seemed to work better, or at least it trained quicker. Now, I could be wrong. I could find that the other way would work better, but for example, I found it trained much differently. So, reward is important because, as I've said before, the agent is trying to maximize the reward. So the reward signal that it gets back is extremely important. So yeah, just think about that. And like I said, most of the problems that you'll be doing early on will be given to you, but anything that you'll do in the future, or custom environments, you'll have to set that reward. And it's something you have to really think about. And I spent a lot of time crafting it and using different mathematical formulas to get something to optimize. And depending on how you frame it, the agent will act very differently. Now, I'm going to go just quickly over just a bit of the Markov decision process, and then I'm going to break it down and go into its main elements. So the Markov decision the Markov decision process is a framework used to help to make decisions on a static environment. So the goal is to find a policy, and typically that policy, what you're trying to do is optimize the action for the state. So an MVP is a Markov reward process with decisions. So it's an environment in which all states are Markov. Now, which I'll go into what is Markov. This is what we want to solve. An MVP is a tuple or a tuple, depending on how you say it. Australians tend to say things a bit different than other people. Where S is our state space. So sorry. The S, A, P, R, and gamma is where S is our state space, A is a finite set of actions, and P is the state transition probability function, which I'll go into a bit more and explain, because typically you don't get that in real-world RL problems. You can maybe sort of estimate it, you may not know it at all. And for example, in chess, you would have no idea. But if it was two cards that you had a choice of the colours, then you'd be say 50-50. An MVP is more powerful than simple planning. It's because it will still choose the optimal actions even if something went wrong along the way. So simple planning just follows a plan after you find the best strategy, which works, but if something, something weird occurs to get to that particular state, it's not just looking at the state and making an action, it has a particular set of rules. So I think that the MVP allows things to be a bit more dynamic, and it allows it to, probably depending on where it is put, to make the best decision once it's trained. What I'm going to do too is just break down. I've just sort of broken down the Markov decision process, the diagram, just to simplify it a bit more, and the main components. So S is a set of states, A is a set of actions. The transition probability is give a particular state, and a action, it's the probability of going to the particular next state or states, based on that. Then you've got the starting state distribution, you've got gamma, the discount factor, which we'll go into a bit more, and reward given a action given at a particular state. Once again, we see that loop again, which is part of reinforcement learning. So as you can see now, how the Markov decision process and the reinforcement learning, how important and how they're so entwined. I remember doing a few courses and just self-study and seeing the Markov decision process and thinking that it was absolute, just didn't think it was important at all. But then once I got into reinforcement learning, it structures it in a way. Probably the biggest thing between a typical Markov decision process is that the transition probability is usually unknown in most reinforcement learning tasks. It's a bit different to say dynamic programming. Now, what exactly is a Markov decision process? To understand a Markov decision process, you need to understand the following. So the Markov property, the Markov process, the Markov reward process, and it's good to know the Bellman equation. I won't go into huge detail on the Bellman equation, just give you a brief overview. I recommend just understanding that quite well because it's also quite important part of the whole process. So the Markov property. So the Markov property states that the future is independent of the past given the present. So basically, in a Markov, it doesn't matter what state you're at that point. It doesn't really matter how you got there because it's looking at the future and it's trying to maximize the reward from that point onwards. So in mathematical terms, a Markov property is only if the state captures all the relevant information from the history. So for a Markov state S and its successor state, the state transition probability function is defined by the code below. It's a probability distribution over the next possible success state given the current state. The agent in some state, there is a probability to go to the first state and another probability to go to the second state. So you are at a state, it doesn't care how it got there, it's trying to maximize the reward, and it's got a probability to going to a particular state based on the actions. And that is very different depending on what task that you're doing. Like I said, once again, chess, probability is almost infinite, but it's probably also at that point, it doesn't matter how it got there, it's there and it has to try to optimize from that point onwards. So that's something that RL and Markov is quite important. Now, the Markov process. So it's a memoryless random process, basically, a sequence of random states with Markov properties, which we talked about before. The Markov process or Markov chain is a tuple or tuple, SP, of the state space and the transition function. So it's not the full Markov decision process yet, this is just the Markov process. And you can see that we're sort of building it at each state. So we first got the state, which is the property, and now we're defining the process involved with the state and probability. So, for example, when we sample an MVP, it's basically a sequence of states, whereas we call it an episode. So that's that episode. So it's going through a particular sequence of states. So, for example, on the diagram on the right, class 1 has a probability of going 50% to Facebook, 50% to class 2. From there, it has 20 and 80% for sleep or to go to class 3. And then when it gets to class 3, it has a 60% and a 40% to go to either the pub or pass. And so when it finally gets to the whole process, when it gets through there in a sense and gets to pass and then goes back to sleep and gets to terminal state, that's an episode. So that's finished, it's completed. You start again, or that's it. So that's the process itself, and this is a good way to define it. Now, the Markov reward process, or MRP, is a Markov process with value judgment, saying how much a reward accumulated through some particular sequence that is sampled. As you can see, that tuple or tuple has now got a reward and a discount factor added to it. So we've built upon the previous, where S is a finite state space, P is the state transition probability, R is the reward function, and it's how much immediate reward we expect to get from state S at the moment. Now, there is a notion of the return GT, which is the total discounted reward from time step T. This is what we care about. The goal is to maximize the return, given the below equation. Now, the gamma is a discount factor So one of the things about discount is that if the discount is set to 0, for example, the agent will only think about the next reward and doesn't give it any care about the future rewards. If the discount factor is set to 1, it is thinking about all the future rewards. Now, typically what we set this to is something close to 1, like 0.99. So it cares about the current one and the future, and has a discount on all those future rewards. So, sort of explain this a bit more and go back to it. So, we talk about the Bellman equation. So, the Bellman equation, and basically an agent is trying to get the most expected sum of reward from every state that it lands in. And even in order to achieve this, it has to get the optimal value function, i.e. the maximum sum of the reward. Now, the Bellman equation will help us to do so. Now, this gives the principles of the Bellman equation in quite simple for you. It breaks it down. So, the value of some state here is the sum of rewards to a terminal state with the reward of each successive state discounted. So, for example, the reward at the next step are taken after given a particular action is then the reward at the subsequent state is discounted by gamma. The reward at the next subsequent state is further discounted by gamma squared, and goes on and on and on. So, and it increases exponentially. So, for example, if, as I explained earlier, here, if y discount is set to 1, so for example here, it gets a reward of 1, and then it gets a reward of 0, but it's 1, 1, 1. If it discount is set to 0.9, so it gets 1, and the next was 0 and 0, but as you can see, it's 1, 0.9, and 0.81. So it's very important to have a discount, like really important, and is used pretty much in most tasks that you'll be trying to do, and also can change the way the agent learns quite dramatically. So next, I'm just going to go a bit more now that we've gone through the processes to get to this point. I'm now going to actually define the Markov decision process in a little bit more. So a Markov decision process is a Markov reward process with decisions. It's an environment in which all states are Markov. This is what we want to solve. An MDP is a tuple, where S is our state space, A is our finite set of actions, P is the state transition probability, R is the reward function, and gamma is the discount factor. Basically, it's then creating a policy and is the distribution of actions given a particular state. So it's, the distribution is, in a sense, what is the, and what it's trying to do is choose the best action to maximize the reward. And so, pretty much what reinforcement learning is. So as you can see, a Markov decision process and reinforcement learning are pretty much the same thing. As a reinforcement learning is usually based on a Markov decision process. Now, I'm just put that information in a bit simpler ways for you to see it. So I've just broken it down a bit more simple. State S beginning with initial state, the action is A. Each state S has an action, or actions, sorry, it's available. Transition model. Now, transition model is typically, honestly, is unknown. Not very often do you know it. You may be able to estimate it based on the amount of actions, but it also could be completely independent and not split evenly. It could be something else, something that you don't know about, which changes that. And the reward, you've also got the reward function, of course, the policy, which is the whole thing that we're trying to create. And a policy in typical reinforcement learning is a table. What we're doing in deep reinforcement, which you're going to get more into, is the policy is created by a neural network. We use a neural network or a deep neural network. And it's more of a function approximation rather than just a pure state action pair in a table. So which allows you then to have, once again, which I explained from the earlier previous webinar, allows to generalize quite well. So, and then there's other techniques to generalize things more. Example, normalizing data can help with that, and there's a few other techniques. So next, now that we've gone over the Markov decision process, this gives you a good foundation to now move on to the solutions and the actual algorithms that you'll be working on. But this is the foundations and probably the main structure that you need to truly understand to understand reinforcement learning, or at least at a high level. Now, this is just a little thing that I've added on to the end, is OpenAI Gym, and how it's sort of why it's important in reinforcement learning, and how it sort of is linked to an MVP and also reinforcement learning. So OpenAI Gym was created developing and comparing reinforcement algorithms, but it gives you a really good framework, RL framework to work from. So I'm just going to click one of the links. So this is the main website. Now I'm just going to go over the basics of Gym and how it is pretty much, a framework for a Markov decision process to a point, or at least for the RL framework. So as you see, it starts off, it's got an environment, it has an observation at the beginning, which is done via the environment reset, which is giving a particular state. And then, for 1,000 steps, as you can see here, it's rendering it and it's performing an action. Now, right here, the action is just a sample. Typically, what that would be is the agent would be performing an action, and this would be based on its observation that it sees. So typically what you'd be doing is, as an argument, adding in the the state so it can make the best decision. Basically on the next step, which is that sequential model which you see in a Markov decision process, each step it gets that feedback, so the observation, reward, and done. Now, done is saying whether the episode has completed or not, and that usually what that will do is reset it and start it again, or just completely finish it. Info can be extra information that is provided, particularly not what the actual agent is getting to learn. Now, if we go into the documentation, I'll go down to is the observation. So basically, an observation typically is an object, reward is a float, done is a boolean, true and false, and info is usually a dict. As you can see, that action, environment, observation, reward loop is shown again, which is the fundamentals of what we're sort of learning. Now, once again, this is that the basic loop that we're going over. Now, this is good to understand and how to port in. So you'd port in your environment, you would change that to be an agent, and that's how you would sort of start your process. Now, the spaces that the main things that you get in spaces, for example, or the observation space, are usually discrete or boxed. So a discrete would be an array. Sorry, a discrete would say an action would be, say 2 buttons, left or right. And an observation space that's boxed would be an array. So that's just an array with 4 elements. For example, this. Now, if the shape was say 4 by 3, it might be all of that information, for example, as one array. For example, pixels, with the RGB would be a big array of data. And also, probably the other thing that you can think of is typically we find that we try to make the actions discrete in the environment, as it makes it much easier. But some of the new algorithms, I seem to be combating that, like SAC and SAC. But you may get an action space that is actually a box. So it might have an array of 8 actions that could be potentially true or false, or and which in turn on. So you could have multiple actions occurring at once. Now, how you could make that discrete is you could combine 2 actions together as one discrete action, and that's used a lot. So, for example, in the retro competition, that was done to simplify the actions of control rather than having combinations. What they did is added, for example, down and a particular button, or forward and jump, and things like that, to try to make it more simple. And it does typically makes it easier to train. So the more actions you have, typically it takes longer to train. And so if it's an array and has all these possible options, that could be quite hard for it to learn. But like once said, some of the new algorithms are doing really, really well, and we're starting to beat this problem a bit better. Now, probably the other thing is we usually define the limits as well. So a lot of times that's infinite on both sides, and just a few other bits and pieces. So, look, what I would recommend if you've got time is look through GIM, because I use GIM even in most of the RL problem, deep RL problems that I am custom building. I just make a custom environment and use a template from GIM. Because it's just easy then to plug in your algorithm. If your algorithm or an algorithm that you're using from, say, some baselines, are usually developed to work with GIM, and so it's not hard to plug your environment into a GIM template and move it there. So, I definitely recommend doing that. Now, hopefully that sort of gives you a bit more of an idea of reinforcement learning and also the Markov decision process. And combination of the course content, a little bit of extra material, and also talking to people in Slack, and myself, hopefully if you do get stuck or don't quite understand it, you can go into a bit more. There's also more, you can reference and look at stuff on the internet and get a bit better idea. Now, we've pretty much got to the Q&A time. So anyone watching has some questions right now, put them forward. And I'll just wait to see if anyone has any questions. Okay, no one has any questions at the moment, which is all good. Hopefully he understood what I was describing. Now, just before I finish up for this webinar, anyone who hasn't booked in a one-on-one meeting with myself, I'd highly recommend booking that in. It allows us, myself and staff at Udacity, to get a bit of a better idea of how we can help you through the course. So if you haven't had a meeting yet or haven't booked one in, please do so as soon as you can, just so we can try to help and craft a learning plan for you, and also helps us understand the best way to plan future webinars and also ways that we can help you. So once again, thank you very much for watching this, and I hope that it was informative and that you got something out of it. And I also thank you, for getting this far. It's a great course with great content, and I'm hoping that you really enjoying it and that you will be able to apply these skills in the future to do some incredible things. Just my final words, I believe that deep reinforcement learning has the capability of changing the world almost more than any other technology. There's a few others out there, but it's one of those key technologies that joined together will make some incredible advances in the world. And probably another note is, if you do learn this, try to use the technology for good. Don't use it for evil. One of the biggest problems that we're facing in AI is using autonomous weapons, and I'm hoping that we have enough students that want to do good and make the world a better place, and that not many people go down that path. Sometimes you could be enticed with lots and lots of money, but I think a lot of the community has good ethics, and a lot of the academic people are looking at trying to make things better for the world. So it's a fantastic community, and I hope that you have a good time learning this. So once again, thank you very much, and that's all for tonight. And I'm signing off. Goodbye.